All right, today I'm going to be talking about input latency, what it is, how it affects your games, and whether or not you can actually do anything about it. Hey, I'm Mason. I'm an independent game developer, a board member on the Zig Software Foundation, and in the past, I taught both grad and undergrad students to make games and game engines. Along those lines, we are going to be talking about custom tech here today, so if you're using an off-the-shelf engine, you may or may not be able to leverage these ideas. Similarly, my focus is on indie games, so a lot of the trade-offs that I'm making are geared specifically towards small games. All right, jumping right in, let's define our terms. What is input latency? Well, for the purpose of this talk, I'm going to define input latency to be the time from the input device being triggered to the output being shown on screen. So for example, if I was to click my mouse to advance the slideshow, and it was to instantly advance, that would be low input latency. On the flip side, if I was to click it and it was to take a couple seconds to advance, that would be very high input latency. So is this actually a problem? I mean, computers these days are pretty fast and they're getting faster. There's a great write-up by Dan Liu, I'll link it in the description, but the TLDR is that input latency has gotten worse over time. And as a programmer, this is something, especially a programmer working on games, this is something you should probably care about. So where's it coming from? Well, there's three main places input latency can come from. The first one is going to be the actual input hardware. To make a silly extreme example, if you had a mouse that only pulled for input once a second, well, it would have up to 1 second of input latency. On the flip side, maybe your mouse pulls for input very often, but has a very long buffer. It might buffer up the data so it can do smoothing on it, or it can do debouncing, other kinds of post-processing. Any amount of buffering it's doing is going to further increase the input latency. Unfortunately, as game developers, there's not much we can really do about this, right? You can't really break into all your players' houses and replace their mice. So let's look at some of the other sources. Software. Well, there's two main places input latency can come from in software. One is going to be high processing time, right? If your game is running at a lower frame rate, that's going to increase your input latency. Unfortunately, while that effect is very real, I can't really just sit here and tell you to make your game faster. Actually, I can. Make your game faster. But you already knew that. You're already trying to make your game fast, and this wouldn't be a very interesting talk if all I said was, well, make your game fast. So what else can we do in software? Well, the other place the input latency comes from in software is the compositor. The compositor is the part of your operating system that decides how to show all the different images from all the different applications you're running on screen. It has the potential to introduce additional latency, but unfortunately that's not software that you wrote or that you directly control. So we're going to cross all that out too. What's the last source? Well, it's going to be the output hardware. The output hardware could have high buffer lengths or do additional processing. Unfortunately, that's also kind of out of our control. So is this even worth worrying about? Kind of sounds like we can't do much about it, and we're probably not building an e-sport anyway, right? Well, I'm going to say yes, this is in fact worth worrying about. So today we're going to talk about why you should care, even if you're not building an e-sport, and what you can actually do. So starting off with why you should care, doesn't this only matter for esports? Well, I actually think that the impact of input latency on esports is overblown. Don't get me wrong. If you're playing esports, you would rather have low input latency than high input latency, for sure. But the thing is, humans compensate for predictable latency. You've ever played drums, right? You can't just instantly hit the drum. You have to lift the drumstick up and then put it back down. That doesn't mean that every drummer plays 500 milliseconds late, right? You know how long it takes you to do the thing, so you start early. In theory, it could give you a competitive edge. But you're also fighting against your actual reaction time, and reaction time isn't a super interesting game mechanic. Most of these kinds of games are really about knowing the meta, about having good strategy, not about clicking the button as fast as you can. It's anecdotal, but I used to play a lot of Armageddon Advanced, and I was pretty good back in the day. Don't get me wrong, I definitely preferred to play on servers with a low ping, but I'd often end up on, servers run on someone's Raspberry Pi in their basement on the other side of the world, and I'd have 400 milliseconds ping, and I still won a lot of matches that way, because that just ultimately wasn't the deciding factor, even if the lower ping did, feel a lot better. On the flip side, input latency's effect on GUIs, and that includes things like card games or simulation games, is, in my opinion, very underappreciated. First of all, there's the discrepancy with the system cursor. Your operating system is going to be blitting your cursor onto the screen at the last second with the most up-to-date position possible, which makes it very, very low input latency. If the rest of your game isn't working that way, you're going to feel the difference. This is super notable if you maybe follow a Vulkan tutorial, kind of set up with the standard options, and then set up something like DRM GUI. You'll notice, man, why does my app feel so much worse than other apps on my computer? Is DRM GUI bad? Well, no, it turns out DRM GUI is great, but your kind of standard setup just has very high input latency, and therefore all your mouse interactions feel really wonky and weird. Secondly, GUIs tend to have weaker metaphors, right? If you're playing an action game, maybe it's not the case for Armageddon, but in general, if you're playing an action game, you're clicking heads. You kind of understand what's happening. It's not really all that abstract. On the flip side, like clicking on the file menu and then moving your mouse down and turning on or off a checkbox, like this is weird stuff. Like as computer users, we've built up understanding of how these UI elements work, but there's way more levels of abstraction between us and the actual task that we're doing, and that means we really want to take anything we can to make it feel more tactile, to make it easier to kind of comprehend. Also, if you can render very quickly, the floor for input latency is much lower, right? A typical user interface should be able to be rendered in microseconds, which means you have essentially a zero floor for software-induced input latency. It would be great if we could take advantage of that. Anecdotally, if I set up a user interface with 1 to 2 frames of latency, at 60 hertz, it feels horrible. It feels sluggish. It makes me not want to use the software. On the flip side, if I get close to 0 plus whatever the minimum amount just caused by the hardware is, it can feel almost magical. Like, you push a button and like right as you're about to push it, you're like, oh wow, the result showed up on screen before I pushed the button. Like it didn't really, but it feels like it did. And I mean, wouldn't you rather your game feel magical than feel sluggish, right? So I think that especially smaller indie games, GUI-based games, you really want to care about this stuff. Now, the best way to convince yourself that the stuff actually matters is to try it for yourself. Unfortunately, I can't really do that for you in a YouTube video because a key component is the actual input. What I can do is I can show you the tool that I built for myself that I use to test this stuff. But just keep in mind, like, you won't be able to feel it since you aren't the one actually giving the inputs. This tool does 3 things. First, it has a vertical bar moving left to right at a constant speed. The idea there is that if we push things too far and start dropping frames, it'll be very obvious because that bar will start to stutter. Or if we end up with an inconsistent delta time or something. Second, it has this white rectangle that attempts to follow my mouse. If we have high input latency, it'll lag behind the mouse. If we have low input latency, it'll catch up with the mouse pretty quickly. That's nice for testing kind of this continuous input latency. And then for discrete, when I click the mouse, I won't do this too much so I don't have to give like a seizure warning. But when I click the mouse, the screen will turn white. And when I release it, it'll turn black, which is testing the discrete input latency. Okay, so fine, input latency matters, but what can we actually do about it? Well, there's 2 main things I'm aware of that we can do to improve input latency. One is configuring our swap chain correctly, and the second is some slightly more advanced frame pacing. The conventional wisdom around swap chains, if you just follow a Vulkan tutorial online, is to use FIFO, maybe FIFO relaxed, or Mailbox. FIFO is essentially just vsync. Mailbox is like triple buffering. And the tutorials will typically have you set up your image count to be min image count plus 1. So this is actually great advice if you're making a AAA game. It's actually pretty poor advice for UIs or games that can render very quickly. Mailbox, triple buffering, is extremely wasteful. Say that your game can render in 200 microseconds. Well, you're going to repeatedly spend those 200 microseconds over and over and over and over again rendering the frame until it's time to show a frame on screen, and then you throw all of them out and you just show the last one. So if the user's on a battery-powered device, you're wasting lots of power. If they're not, you're still heating up their computer for no reason. And you're potentially introducing jitter because there's no fixed rate at which you're rendering. You don't know how long your delta time should be. Alternatively, if you take the suggestion to do FIFO with min image count plus 1, that min image count plus 1 means you're doing 1 extra frame of buffering that you didn't need to do. That's an extra 16 milliseconds of input latency at 60 hertz. All right, so what's my recommendation? Well, I recommend using FIFO relaxed and setting your image count to min image count. Now, if you do this, you're going to get best practice validation warnings. These aren't correctness warnings, they're best practice warnings. If you have the Vulkan layer set up, which you should, you have to ignore these. Whenever anyone tells you a best practice, you have to ask yourself, best practice for who and why? In this case, for a very graphically intensive game, it is a best practice. By having your buffer be slightly longer, yes, you increased your input latency, but also it means that if you're a little bit late on one frame, you can just make up for it on the next frame and the user will never actually experience the dropped frame. That's great. It's a very reasonable trade-off to make for a very graphically intensive game. If your game isn't very graphically intensive, this is a very poor trade-off to make. You're increasing your input latency with no actual benefit to the end user. So if you get this set up right, at 60 hertz, you're going to save about 16.66 milliseconds of input latency, which is great, right? Just by changing some options. We didn't even have to write any new code. Link in the description to a Vulkan example of this. The other way we're going to improve our input latency is through frame pacing. So we have a standard game loop here, right? While true, we pull for input, we update the game, and then we render the game. And what we're going to do is we're actually going to insert a call to sleep somewhere in this function. And in doing that, we're going to decrease our input latency. Sleep? Why would sleep decrease our input latency? Well, I encourage you to pause the video and see if you can figure out why that would work and what line you should actually put the sleep on. All right, well, if you're ready, the answer is we're going to put the sleep right here, right before pull. Okay, so what the heck? Why does that work? Well, if you think things through, assuming that we're using vsync, there's going to be a sleep whether you like it or not, right? At some point, you've generated as many frames as it can be queued up, and the next v-blank hasn't happened yet, and you render your frame. The driver is going to make you wait, but it's going to make you wait down here after you've already pulled for input. That's bad news, right? You've already pulled for input, and now you're increasing the time between when that input sample was taken and when the results of that input are actually shown on screen. What you'd much rather do is move that sleep to before the pull so that you wait until the very last moment, you're about to have a v-blank, and then you go, oh, time to get the input, update the game, and then render real quick right before the v-blank, and then you're done, right? That is going to be the lowest input latency you can get. Now, of course, the killer question here is how much you need to sleep so that the driver won't sleep. Here's a little diagram. You can see that my game update is right here. It's very quick. This whole time up front, we're just sleeping. And then afterwards, there's a little headroom that I left intentionally just to make sure I don't overshoot. So how do we know how long to sleep? Well, ideally, we would just use VKEXT present timing. But unfortunately, the support for this is not very widespread yet. So we could also look into VK-AMD anti-lag or VK-NV low latency, but unfortunately, neither of them appear to function properly. I did try reaching out. I can't remember whether it was to AMD or NVIDIA, and I didn't hear back. If you have managed to use these to correctly find out how much you need to sleep to minimize input latency, hit me up in the comments. Would love to know if I'm just doing something wrong. Regardless, that leaves us with one option, which is we guess, but we're going to make an educated guess. So here's my frame pacing heuristic I've been using for my game that's been working well for me. Our goal is to minimize what I'm going to call slop. I can't remember for sure where I got this term. I want to say it was from a write-up by the Call of Duty devs, but I could be mistaken. Slop is going to be the time the CPU spends blocking on the GPU after input. Ideally, we'd like this to be 0. We'd want to sleep before pulling for input. To minimize this value, we need a way to measure it. And there's a little bit of a gotcha here. The driver is allowed to sleep in 2 different places. It could sleep when presenting the frame, or it could sleep when acquiring the next frame. And so you got to make sure you time both of these. Your particular setup might always introduce the sleep in one place or in the other, but that's just your setup. And I've also seen setups that do it in both for some reason. So yeah, be careful of that. Make sure you're timing both. And we're assuming a FIFO swap chain here. This doesn't really make sense otherwise. And then we're going to calculate sleep as the minimum of slop minus headroom and refresh period minus headroom. The idea being that we need some headroom to avoid a positive feedback loop if we overshoot, and you never should be sleeping more than the refresh period minus that headroom, so that prevents this kind of worst case scenario failure of the heuristic. If we set things up like this, it can decrease the input latency by another 14, 15 milliseconds, counting for a couple milliseconds of headroom. Another link in the description with some example Vulkan code that does this. If we combine both our swap chain changes and our frame pacer changes, we get a total of 30 milliseconds of input latency reduction at 60 hertz, which is great. That's enough to take a slightly sluggish feeling application and make it feel snappy. I also want to give you a few quick implementation tips. First, don't guess, measure. You really want to know how long stuff is actually taking. You want to know if the changes you're making are having the expected effects. Also, you should really build a latency test scene like the one I showed earlier. It's one thing to see the numbers in a chart. It's another thing to see if they feel the way that you expect them to feel. Ideally, they feel the way you expect, and they also are the numbers that you expect. Lastly, be on the lookout for better OS support. If we get widespread support for that Vulkan extension I mentioned earlier, this stuff will all get a lot easier. Well, that's all I got for today. Thank you for watching. If you enjoyed this video, consider signing up for my newsletter at gamesbymason.com/newsletter, or checking out my last video. It's not about the API, fast, flexible, and simple rendering in Vulkan.